So our penultimate speaker is Pete Hunt. Pete is head of web engineering at Instagram. He previously worked mainly at Facebook, on the main Facebook. He's a core contributor to ReactJS. He is a guitarist, plays a bit of alternative rock, and he'll be talking today about ReactJS's virtual DOM. Let's give him a warm welcome, Pete Hunt.
Thanks, man. Hey, guys. How's it going? Woo! Everybody get pumped up. Come on. Nice. So my name's Pete. I head up web engineering at Instagram, and I contribute to a library called React. And I'm going to talk to you about the secrets of the virtual DOM. This is the most dramatic title I could come up with for a presentation about software engineering, so work with me on this one. So React is the library that powers a lot of features on Facebook. Graph search, page insights, a lot of data visualization on Canvas, a lot of stuff on our mobile site, including but not limited to photo uploads, search, and all of Instagram.com is one giant React component. But I'm not going to teach you how to build stuff with React today. This isn't going to be a tutorial. Instead, I'm going to focus on the underlying ideas behind React rather than specific implementations. And I'm also going to talk about competing ideas and try to stay away from those underlying implementations as well. So, does anybody here build user interfaces? All right, basically everyone builds interfaces, whether they can raise their hand or not, I feel like. So they're really difficult to build. And they kind of feel like they're more difficult to build than other types of software. And one of the reasons for that is that it just doesn't feel right when you have a bug. So a lot of times I'll try to get it as close as I can, and I'll hand it off to my PM, designer, or we'll test it with some users. And there'll be a lot of complaints that we didn't find before handing it off to them. And the reason why it's very hard to ensure quality when you're building user interfaces is because humans are in the loop, first and foremost. So it's very difficult to write an automated test for this looks correct. We can do Selenium tests and we can do unit tests, but it's hard to get the entire picture from a unit test. So for example, we have a bunch of test cases covering our mobile site for photo uploads. And one time we started getting bug reports in that photos weren't loading on our mobile site. We looked at our egress graphs, the JPEGs were being served, our test cases were all passing, but it turned out that somebody had committed a line of code that set the height of the images to 0 in CSS. It's very difficult to test for that unless you were either using a screenshotting system or you thought of that ahead of time. Additionally, we've got designers that are working really hard to build user interfaces that seem simple to the user. But underneath that veneer of simplicity, there's usually a lot of complexity as well, a lot of state that you need to manage to provide the right user experience. And finally, the tools that we have today for building software aren't as good as they are for building backends. So unit testing I mentioned, but there's also things like static analysis. It helps you find some classes of bugs, but usually not the types of bugs that you find when building UI. You know, you got the math wrong on the layout. It's very hard for you to apply static analysis for that. And you know, even like type checking is helpful, but it doesn't get you all the way. But at the end of the day, user interfaces are just really complex things to build. The good news is we're programmers, and our job is to organize complexity. So Jeremy beat me to the Dijkstra quotes today, but I got plenty of them. So the art of programming is the art of organizing complexity, of mastering multitude, and avoiding its bastard chaos as effectively as possible. One technique that we found, one of the most important techniques we found, is to focus on being predictable. I want my app to break the same way in development that it does in production. And I want to be able to reproduce the state of my application without doing too many imperative operations that are difficult to test and reproduce. So another word for this could be reliable. So let's focus on making our user interfaces more reliable. What do we need to do? So I go back to Dijkstra, and I asked Dijkstra how to do this. And he says, we should do our utmost to shorten the conceptual gap between the static program and the dynamic process to make the correspondence between program and process as trivial as possible. Now I'm going to try to illustrate that. So hopefully you guys are still pumped up from your coffee break. So here's a screenshot of our buddy list. And I'm going to ask you what the state of this buddy list should be after I read off a series of interactions, OK? So go memorize what this looks like. Remember who's in the list. You guys ready? Come on, you ready? Let's get pumped up. All right. Alice went offline. Bob went offline. Steve went online. Bob went online. Charles is idle, and Charles is on mobile. What does it look like? It's very difficult for humans to visualize processes that evolve over time. You've got to keep all of this state in your head, and you've got to basically write down what happens and manually update this model. Instead, it would be a lot easier for us to visualize what the buddy list should look like if we looked at a consistent snapshot of the data at this point in time. So if you look at this, it's probably a lot easier for you to visualize what that list should look like. So the state of the art for doing this today is something called data binding. Does anybody here use data binding? Wow, I would say most people here are using data binding. Awesome. So what data binding basically does is it makes the user interface, which is one dynamic process, look a lot more like a static program relative to this other dynamic process, which is your underlying data model or domain logic or whatever you want to call it, that's being influenced from user events and the network. So at the end of the day, it's just syncing one data model with the user interface. So one way I like to think of data binding is as a polyfill for reactive JavaScript and the DOM. So if you're familiar with reactive programming, there was a talk on RxJS earlier today. It's basically programming that responds to stimuli. And this is a polyfill for that. Now, data binding is certainly a non-trivial abstraction. And all non-trivial abstractions are leaky to some degree. I don't think the data binding that we have today is simple. At Facebook, we had a traditional kind of MVC data binding system. And as we started to build with it, the complexity snowballed to the point where we couldn't maintain our applications anymore. So we started looking for another solution. But I'll get to that in a second. Dijkstra also says that simplicity is prerequisite for reliability. So the goal here is to make reliable, predictable software. But we can't predict what we don't fully understand. So we have to be able to fit it in our heads. And in order to fit some software into our head, it has to be simple. Now, simple is one of these words that's thrown around all the time and can take on a lot of different meanings depending on who you're talking to. So this guy, Rich Hickey, invented this language called Clojure. And he has a really good objective definition of what simplicity is. And he says that simplicity is marked by the lack of interleaving. So if you think about those times when you're trying to solve a problem and you look at a piece of code, if it only does one thing, you only need to hold that thing in your head to understand what it's going to do and predict what's going to happen. If it has a bunch of different things intertwined into it, you need to start reaching to other parts of the program and understanding a bigger chunk of it before you're able to fix that bug or add a new feature. Now, it's important to note that I'm saying simple, I'm not saying familiar. So I'm going to talk about a couple of ideas here. Some are more familiar than others. Just because something might not be familiar doesn't necessarily mean that it's not simple. And something familiar may not be simple either. So I ask you to keep an open mind. So the first idea I'm going to talk about is something called key value observation. So this is the type of data binding implemented by Ember, Knockout, Backbone, Meteor, pretty much most systems out there. And it's not just limited to the web either. This is how Apple implements data binding on iOS as well. And it's built around the idea of observables and computed properties. Now, the way I'm using observable here is not the same way that observable is being used in the RX talk. They have a slightly different definition. The way I'm using it is an observable is a value that can notify other things when it's changed. So it has an on-change event associated with it. Computed properties are very similar, except they depend on other observables. So a computed property could be combining two observables into a sum, and that would be the computed property would be the sum. So let's walk through an example of how we build a system with this. Imagine that we have this data structure coming from the server, and we're going to build a review site for companies, like a Rotten Tomatoes type thing. So I'm not a very good designer. This is the UI I came up with. What we're going to do is we're going to show the most popular companies sorted by the total number of votes. We're going to take the top 3 by popularity, and we're going to show a rating based on the percentage of votes that were upvotes. So I'm going to show how we would implement this in KVO. And I'm going to use Ember as this example for KVO. The reason why I chose Ember is because they're a really talented team, and they're focused very, very intently on developer experience. They're starting to be focused on performance as well. So the way I see it, if this team can't get KVO right and make it simple, then there's probably something wrong with the underlying idea. So let's walk through this. This is implemented in a language called Handlebars, which is a domain-specific language for gluing Ember's notion of observables to DOM nodes. And the way that it works is that we have this each directive up here, and it iterates over everything in this top companies list, and it renders some DOM nodes. Now, note that we're not able to use arbitrary JavaScript expressions here. This is all a custom domain-specific language, which isn't as powerful as JavaScript, because JavaScript is not reactive, and the DOM is not reactive. So this is a leak in the abstraction that we have to build a domain-specific language to do this. But let's move on. There's JavaScript underlying this view as well. So we'll start by creating a function that sums the upvotes and the downvotes to get the total number of votes. Now, in Ember's implementation, you use getters to pull values off of models. But that's just a specific of the implementation. We model each company, and each company has a computed property, like I mentioned before. And that's that percentage score. And the way that we compute that is we divide the number of upvotes by the total number of votes, and we convert it to a percentage. Now, take a look at this .property right there. That indicates that it's a computed property. And this tells the system, hey, whenever the upvotes or the downvotes change, make sure that we recompute this score computed property. And when that score computed property recomputes, it will update the DOM as well, because it has things observing it as well. So moving on, we build our overall application model, which has that top companies array. And the way that we implement this is we have this companies raw array, and we sort it by the total number of votes, and we slice off the top 3. And finally, we add a little bit of glue code to glue our JSON data structure that we got from the server into Ember's system. So here's a video of the test case that I ran, where I deployed this application, and I randomly added a number of upvotes and downvotes to each of 100 companies every half second or so. And here's it working. You can see the percentages live updating. But since I'm adding a random number of upvotes and downvotes to each of 100 companies and showing the top 3 by total number of votes, you would think that this list would be constantly resorting. So I really appreciate the code review you guys gave to me, but we pushed it to production and we screwed everything up. So, geez. Here's the bug. You wouldn't have thought that this is a bug. And the reason why this is buggy is because we're only observing the list itself. So only when the length of the list changes will this be recomputed. We actually have to dive into each item and observe the upvotes and the downvotes inside of each item in this array. Now, first of all, there wasn't like a compiler time or a runtime warning that could help me out with solving this. Additionally, this is a domain-specific language for expressing these relationships. So no static analysis tool understands it. But what's most important is that I can't look at this function and figure out how to make this properties expression work correctly. I have to dive into the implementation of that total votes function. That's more of the program that I have to load into my head to solve this bug. It's more interleaving, and it's not simple. I have to know how the data binding system works for any piece of code that touches my data. So when I make that fix, everything resorts, and it works fine. Now, if you've worked with Ember before, you probably think that I don't know what I'm doing, because I should have made that total votes a computed property on the company. It reminds me of this quote from Einstein that says, "Intellectuals solve problems, and geniuses prevent them." With a traditional key-value observation system, you are not allowed to use traditional JavaScript functions to compose your application. They don't work. I don't like that. So let's look at another system, which I think improves on key-value observation, which is dirty checking. This is implemented most popularly by Angular, but it's also implemented by Polymer as well with object.observe. Now let's imagine we want to build this very common widget on Facebook.com, which is a profile picture with a username attached to it. The markup looks pretty great. We have a controller, and then we reference the reusable component we're defining. And in Angular, it's called a directive, and in Polymer, it's called a custom element. So here's the initial kind of boilerplate code we need to set it up in Angular. If you're not super familiar with Angular, the specifics aren't crazy important. We have this scope variable, which holds all of the data that's being tracked by the system. And when it changes, it'll trigger re-renders. We then define the avatar component. Now, on Facebook, we have other pieces of user interface as well, or one component is called a face pile, and it's just a bunch of profile pictures. So it would be great if that component and my avatar component could share code. So rather than put all of the code to render that UI in this directive, I'm going to split it into two directives, one that renders just the picture, called FBPic, and another one that renders the avatar, called FBAvatar. Now, notice in order to compose my application here, I have to create a string representing the parameters that I want to pass to this directive. And then Angular is going to stick that into the DOM, reparse the DOM, and pull it back out, and then run this pick. And the data doesn't flow in any way similar to how it flows in JavaScript. We set up these two-directional data bindings using these scope indicators here. And it breaks all your static analysis tools. And it's just not the way that you compose programs in regular programming languages. It's a leak in the abstraction that you have to use directives to compose your application in Angular. Now, the point isn't that we can't build applications this way, because people build them all the time. It's that these crazy talented teams at Google and Ember can't make this simpler. So I wonder if we can't create the same things with drastically simpler tools. So imagine for a second that we had a reactive JavaScript built into the browser today, and we wanted to build this example. It would probably look something like this. We'd have a little bit of boilerplate code to fetch the JSON, and we'd tell it which DOM node to render into. We'd create a function to compute the total number of votes, and then we'd start creating DOM nodes. So in this example, I'm going to spare you the document.createElement boilerplate and simply call methods named for each HTML element on this DOM object. So we'll create a DOM node, and we'll sort the companies by the total number of votes. We'll take the top 3, and then for each company, we'll render a list item with the title, and we'll embed a JavaScript expression in there that calculates the percentage. And the system will know how to keep that up to date magically, because this is a magical reactive JavaScript. Now, let's suppose that we don't like all of this nesting here. We can pull it out and flatten it out, just like you can with any sort of JavaScript program, by making a function and composing your application with functions. And oh, by the way, this is a lot easier to unit test, too. We can now unit test the row component separately from the application itself. Now, unfortunately, we can't do this today. And the reason we can't do this today is because JavaScript isn't reactive. And even worse than that, the DOM is stateful. So we can't simply just destroy the DOM and recreate it all the time, because it's going to lead to poor performance and a bad user experience. Imagine you're scrolling and suddenly we destroy all the DOM nodes and recreate them. You're going to have a bad time. So over the past couple of years at Facebook, and now in open source, we've been building an abstraction around this that we like to call the virtual DOM. And we think of it as a much less leaky polyfill for reactive JavaScript in the DOM than key value observation or dirty checking. So spoiler alert, this is actually valid React code today, and it works in the browser. And I think I'm going to be adding, by the way, the today count is going to start going over the future count with this talk, because everything's available today. So I want you to look at this code and realize that we can use our full JavaScript toolbox here. We can use all the tools of today to compose our application. And there's not a single data binding artifact here. You don't have any idea what sort of data binding system you need to use to keep things up to date, because you're just writing JavaScript. Now, this seems kind of magical. But that's because we treat your code like a black box. And here's how it works. Whenever anything changes in your application, the virtual DOM, and the reference implementation is called React, will re-render everything to a virtual DOM representation. Then what the system does is it diffs the current virtual DOM representation, computed after the data changed, with the previous one, computed before the data changed. Then we diff those two representations, we isolate what exactly changed in the virtual DOM, and we only update the real DOM with what actually needs to be changed. This makes your applications a lot more expressive. And when I mean expressive, I don't mean the breadth of ideas like the traditional expressive power definition. I like to think of practical expressivity, which is a measure of ideas expressible concisely and readily in the language. So like I said, when we treat your code like a black box, it makes your code simpler. You don't have this data binding concern intertwined with the rest of your application. So we've recognized that there are some problems with traditional data binding systems. But the reason why nobody does this alternative approach is because until recently, people have thought that it won't perform well. And if you think about it, it kind of intuitively seems like it won't perform well, because we're doing all of this re-rendering and diffing of things that may not have changed. But I've got great news. That quote's actually originally about Lisp programmers. Sorry, David. But every system has constraints, right? Every one of these abstractions is leaky. And we like to think of the virtual DOM as the set of leaks that we would prefer to have as opposed to these other systems. So with KVO, your app code is entangled with observables. You need to know about how the observation system works at every single part of your application. With Angular-style dirty checking, it's a little bit better, but you still have to compose with scope and watches and directives. And the leak with the virtual DOM is that you need a signal to say, hey, something changed in the application. And that's a much more manageable leak because it's pushed to the edge of your system. You only need a signal from the outside, and the inside of your code base, all the meat and potatoes of your UI rendering, is unaffected by this. And that signal can come from anywhere. It can come from object.observe, it can come from a browser event, it can come from a network request. In OM, I believe they use request animation frame to signal this. And there's some real benefits for avoiding kind of these domain-specific language approaches that you have to use with KVO as well. Static analysis, so linting, minification, and type checking. When you're putting symbols and strings, these systems won't understand that they're symbols and not strings passed to the user. So you start to have problems with Google Closure Compiler advanced mode, or trying to use TypeScript on an observable list. It's very difficult. So let's talk about performance a little bit. The way that we look at performance today is a little bit different than the way we looked at performance a few years ago, because mobile's a big deal. And memory is just as important, if not more important, on mobile than it is on desktop, or is more important than CPU on mobile. So if you think about it, if you waste a lot of CPU on mobile, you're going to have a sluggish application experience, and your user's going to be mad at you. But if you waste a lot of memory on mobile, the operating system is going to kill the browser process, and you're going to have no user experience. It's not going to be fun. So with key value observation, you've got these observables and these computed properties. And you have to maintain that entire dependency graph. So you need to know that this computed property depends on that computed property, depends on this observable. And so that takes a decent amount of memory and CPU to maintain that representation. Now contrast that with the virtual DOM approach when we're re-rendering all the time. The render code is usually very cheap that you're using to render your user interface. Because if you think about it, there's not really a lot of tight loops in your render code. And if there are, they're generally cacheable. More importantly, your view is almost always smaller than your model. So in complex performance-sensitive applications, you may have lots of data, but you're only rendering a couple items. This is one of my favorite quotes. So I'm going to dive in to some actual performance numbers. Now, measuring performance is very difficult, and I just didn't have the time to do a comprehensive assessment across all platforms, frameworks, and ways of implementing things. So I'm going to use these numbers mostly as evidence of big O complexity, rather than comprehensive, millisecond by millisecond comparisons of these implementations. Because we're talking about ideas, not implementations. So let's go back to this example from before. I implemented this in the production version of Ember as an example of KVO, and the production version of React as an example of virtual DOM. Now, I didn't have time to build it in Angular, and I didn't think it was really worth it because KVO is on this side of the spectrum, virtual DOM is on this side of the spectrum, and Angular is somewhere in the middle when it comes to performance characteristics and the differences of how it's implemented. So when I ran the numbers at 25 items, 25 companies in that list. Now remember, we're taking the top 3 companies and we're displaying them. And so there's 25 underneath that UI. Doesn't matter. You know, these numbers are like within a millisecond of each other, and they're all under a frame anyway, so who cares? When we bump it up to 10,000 items, we start to see a pretty big difference in performance. I mean, it's not only in the initial render time, it's also warm updates and steady-state memory after garbage collection. Now, the reason for this can be found in big O notation. Now, is everybody here familiar with how big O notation works? Everyone knows everything there is to know about O of n? Okay, it's linear. Well, it turns out it matters what this n is. So let's break it down into O of v, which is the size of your view, what you're actually rendering, and O of m, which is the size of your model, kind of the data you've downloaded from the server, or the representation you're maintaining behind the scenes. And what we found is that for applications that are performance sensitive, you're rendering a lot less of the data model than actually exists. So I'm thinking about the past couple things that I've optimized at Facebook, which is our mobile search product and a big sortable data table on desktop. They're rendering a finite number of search results, but they may have thousands of search results cached. So if we were to break it down in kind of a hand-wavy way with big O notation, you would see that KVO can update in constant time. Virtual DOM updates in linear time as a function of v. But one of the big differences here is memory usage. So maintaining that representation of all of your computed properties and observables gets to be really expensive when you use KVO. Whereas with the virtual DOM, we simply sort once and save those top 3 items that were rendered, because we don't have to track the observables throughout your entire application. So we at Facebook found that this O of m here is very, very difficult to scale. So that was a pretty favorable situation for React in the virtual DOM. Let's look at one that's a little less favorable. Let's look at one where we're rendering a lot more nodes than our underlying data model, and let's update a single one of them. So this is kind of the needle in a haystack approach, right? So you would think that re-rendering is generating a lot of nodes we don't have to generate, and then we're walking all of them, and that's a lot of diffing that we don't necessarily have to do. Whereas with KVO, all we have to do is trigger a single callback and update it. Let's see how they compare. So we're going to render 1,000 data items and then render an additional 10,000 DOM nodes. So you'll see here that, that virtual DOM actually does OK in terms of initial render and steady-state memory. But just as you would kind of intuit, the warm update is pretty slow relative to KVO. And this isn't just like, you know, textbook slow. This is way bigger than a frame. So it's actually noticeable by the user. So if we were using a data binding system and we had a performance problem, what would you guys do? Anybody? Sorry? Caching? Well, in most data binding systems that I've used, which is Angular, the advice is to use something called bind once, which is effectively caching the value at the initial state. So I like to think of that as disabling data binding, because if you're caching the value and you're never updating it, it's not really dynamic. But with virtual DOM, you would use memoization and traditional caching techniques to get this performance. And so let me give you a little illustration of that. With React, we provide a hook that says, hey, memoize this component. And it's implemented as a function that takes the previous version of the data, the next version of the data, and it returns whether it should update or not. So if we add these 6 lines of code to our application, all it does is say, hey, if the upvotes or the downvotes have changed, return false. Or, yeah, whatever. I'm jet lagged. We can bring down performance to below a frame. So this is still 10 times slower than KVO. But it doesn't matter, because this is a worst-case scenario, and it's still under 1 frame difference. So we're talking about losing a lot of really attractive properties, like that O of M memory usage is just not as good as O of V memory usage. And the simplicity of pushing that data binding concern to the edges of your program. And you're doing it just to gain under a frame of time. So the secret of the virtual DOM is not about performance. It's about simplicity. We want to build sophisticated applications, applications that are very difficult to hold in your head. In order to make it possible to do anything with them and predict what they're going to do, we need to keep things simple. And I think that the virtual DOM leads to more simple architectures. And because it leads to such simple architectures and treats your code like a black box, it's the most expressive way to build an interface in JavaScript, bar none. So remember our example from before. We had to know about this data binding abstraction all throughout our code base. We're not allowed to use functions to compose our application. We have to use a domain-specific language that was developed, over the course of a year to model your binding between the DOM nodes and the JavaScript. Or you could use dirty checking, which is, you would use this unit of composition for your application rather than this unit of composition for your application. Now, I don't like getting into the lines of code, kind of code golf wars, but I do think that orders of magnitude can illustrate fundamental properties about ideas. So if you look at the bindings for Angular to a popular library called Firebase, there are about 1,018 lines of code when I checked this morning. The equivalent React bindings are 78 lines of code. Now again, arguing about lines of code isn't really productive, but the orders of magnitude here suggest that there's an impedance mismatch between the way that Firebase thinks about data in terms of regular JavaScript and the way that Angular does in terms of its observable kind of directive-based model. So performance is not the main goal of what we're doing here. Simplicity is. But when it comes to performance, most workloads are just fast out of the box and you don't have to think about it. But in the worst case, it's easy to optimize within one frame after you're done building your application without breaking out of the fundamental abstraction. So I ask you, please don't trade simplicity for familiarity. Try out some alternative ideas. See how you like them, poke holes in them, and we'd love to hear feedback about it. Thank you.
Hello.
Hey.
Yeah, this is new for me, the virtual DOM, and my question is, do you use all DOM manipulation with the virtual DOM, or do you go down to the real DOM and do animations or changing an attribute over time?
So the question was, at which point do we drop down to the real DOM, the real browser DOM? So we render these virtual trees, which don't actually use the DOM API themselves. They're basically just JavaScript objects that say, hey, I'm a tag of this type, and I have these attributes or properties. What React will generally do in most cases is just walk that representation and find what changed. And that is executed kind of at whatever time you see fit. So OM executes it on request animation frame. React, out of the box, executes it synchronously. Now, in the case of animations, you can implement animations in terms of that, but a lot of people want to use jQuery plugins or something like that to implement kind of their existing, whatever animations they want to do. And so we provide lifecycle hooks that let you say, hey, here's the, at this point, I'm going to update, do your custom DOM manipulations. So we provide a way for you to do that in a managed way. Does that answer your question?
Yes, thank you.
Cool.
Yeah. One right at the back corner there.
Hi. And one of the things when you're managing, so you see a state going into one view, but some of the complexity, like in a single-page app, is when you've got lots of views talking to each other. Mm-hmm. And normally people handle this through PubSub up to a point. But how does React deal with this kind of managing state across things of an equal kind of tier in your view hierarchy?
So the question was, how do you manage the state and communication of lots of components on the page? Yeah. So the beauty of this abstraction is that it's a fairly lower level abstraction. So it's more like a declarative jQuery. Even though the word declarative doesn't mean much, it's an easy way to think of it. Something that sits more at the jQuery level. So you can implement any sort of communication paradigm you want. So what we tend to do is we have a high-level coarse-grained pub sub that communicates to the various apps on the page. And then within those, we use composition to build the rest of the application. And composition with React basically lets you, automatically update the data whenever the data is changed. Did that answer your question? Cool.
Got one last one? No? All right, brilliant. Thank you, Pete.
Cool. Thanks.